Ladies and gentlemen, welcome to the second lecture from this new chapter on the inner product spaces chapter. In fact, today we'll talk about the actual inner product spaces, and we will see that the model that that we talked about last time for Rn will serve as a good ingredient for the actual inner product spaces. So let's start. And in this lecture, we will be interested to determine whether a function defines an inner product and find the inner product of two vectors, let's say in Rn or in the space of matrices, m by n matrices, or in the space of continuous functions. So today, for the first time in this lecture, we will also introduce some calculus, some integral calculus, and we will introduce basically the space of continuous functions on a closed and bounded interval. Okay, well, last time we talked about the concept of length, of distance, of angles, and we have seen that in R2, in Rn. And in this lecture, we would want to extend that. We would like to extend the concepts of length, distance, angle. So we want to extend these three concepts from Rn, right? One step further. So we want to extend them a little bit to general vector spaces. So instead of having Rn here, we'll have a general vector space. And once we plan to do this, you will see that we're dealing with the inner product space. Anyway, now let's see the details of this. Like I said, you are from the previous lecture, you're already used with you're familiar with the inner product, with the dot product, sorry. And so we are familiar with dot product in Rn. And right, and the dot product called the Euclidean dot product. Let's call it like this. Right, and we have seen the properties of this. Well, basically, it's just one of many other dot products that can be defined on Rn. Well, and now we would like to define another product, which we'll call the inner product. And this will be defined in V. So it will be inner product in vector spaces, in a general vector space. And we will see there will be infinite dimensional vector spaces, even, or finite dimensional vector spaces. Anyway, so this is what we're going to deal with. And now, because I want to distinguish between the two right from the beginning, I would like to make a notation so that it's quite clear how to distinguish between the dot product in Rn and the inner product in a general vector space. Let me denote this by with so this will be u dot v. As you have seen, this is the dot product and I mean Euclidean dot product in Rn. And now the second one, I will denote it in this way as right angle or left angle bracket and right angle bracket, whatever you want to call it. I will denote this by the, let's say, the general inner product for a vector space V. Space V. Okay, so once we have these notations, well, we would like to see if all the properties that we have seen in previous lecture are still valid if for this general inner product in a vector space V. In other words, we would like to see if this inner product will be bilinear, if it's symmetric, whatever, or if we still have a Cauchy-Schwarz type inequality, or a triangle inequality, or a Pythagorean theorem, and so on. We'll see that, in fact, this will be true. Well, just like I said, a general inner product is defined in the same way as the general, that the general space is defined, right? Let's write the definition. Okay, and we'll write the definition of an inner product. Okay, now we'll consider vectors, let u, v, and w be vectors in a vector space V. Like I said, I don't say anything about the dimension, it doesn't matter. And let's call K be any scalar. It can be a real scalar, complex scalar, but anyway, let's assume it's a scalar. We say that an inner product on V, right, is a function that associates, let's write it like this, associates a real number let's call it this a real number, this product U between U and V, with each pair of vectors U and V that satisfy the following axioms. Following axioms below. Okay, and let's see the axioms. We would like to see, you will see that they're very similar as with the ones that we, for the dot product in Rn. The first one is, of course, we have seen the dot product is symmetric, so you can expect the inner product to be the same. UV is the same as VU. The second one, U and V plus W is the same as UV plus U, the inner product between U and W. And the third one, as we need some scalars here. If I have the scalar k times the inner product between u and v will be nothing else than just ku v. Well, if you combine these, okay, the first one, it says that the inner product is symmetric. In fact, let me write like this. We have symmetry. And the second one and the third one tells you that the inner product is bilinear. We have bilinearity. And now the fourth one, of course, the dot product, let's say between v and v, will always be non-negative, with equality if and only if the vector v is 0. If and only if v equals 0 is the 0 vector. All right, so these are the 4 axioms. So this is basically the definition of an inner product. Let's look at it. Right. And now let's see some examples. But before that, I want to point out a remark. A vector space with an inner product, endowed with an inner product, let's say like this. With an inner product is called an inner product space. Sometimes it has a name, Hilbert space, but anyway. Well, from now on, whenever we refer to an inner product space, we'll assume that the set of scalars are the set of real numbers. So all the scalars that we're going to talk about from now on, they're real numbers, right? Okay, now let's see some examples. And the first example I have in mind, of course, which is obvious at this point, since we tried to generalize the dot product in Rn. Well, the dot product in Rn satisfies the axioms from the definition of an inner product. Well, it's quite easy to see this, right? In Rn, keep in mind that the dot product, let me remind you that the dot product between two vectors, vectors, let's say u, which is u1, u2, un, and v, v1, v2, vn, is given by well, u dot v is u1 v1 plus u2 v2 plus u and vn. Well, it's quite clear once I define it like this. It's clear that, in fact, this is the inner product in Rn if you want. basically the dot product here in Rn, you can say that the inner product, when you take the vector space to be Rn, the inner product will become the dot product. Okay, that's easy to see. And you can check the axioms for this dot product here. Very easy to see. I'm not gonna do it. Okay. Now let's see, well, maybe this is the standard inner product, but what if we have something, maybe something, a different inner product? And now let's see another example before I move to the space of continuous functions, because this is where I'm heading to. So I will introduce something new in this lecture where I kind of avoided it as much as I could to introduce some differential calculus or integral calculus until now, but starting from this lecture, I will need this, and you will see why, because I will need it for the Gram-Schmidt orthogonalization procedure, and there will be some calculus involved, especially in the examples that we're going to talk about. Okay, the next example that I have in mind, let's say it's a different type of inner product for R2. So let's say we have two vectors. So in R2, let's consider this vector U, U1, U2, and V. The inner product is given by, well, now we have, I'm gonna write it like this, U dot V will be U1, V1, and now I'm just gonna define it with different times 2, U2, V2. Well, we want to see if this, in fact, let's show that this defines an inner product. So show that this actually defines an inner product. Okay. Well, it's quite clear what we need to do. Since we want to show that this guy here is in fact an inner product, what we need to do is just to verify the 4 axioms from the definition. So let's look at them again. That's the definition of, so we need to verify these 4 axioms, right? From the definition of an inner product. Let's do it. And let's start with the first axiom. Let's verify this one. Well, the product, well, it's quite clear by the way it's defined. As you can see, I have the product of real numbers here, and then I sum them up. Well, the product of real numbers is commutative. So clearly this guy UV, which is U1 V1 plus 2 times U2 V2, will be clearly V1 U1 plus 2 times V2 U2, which is nothing else than the inner product between V and U. So clearly this is commutative. It's obvious, basically. And now let's show the second one. If you look at the second one, was to show that we have some kind of bilinearity. Well, you can combine both of them at the same time. But anyway, let's do it step by step. So the second one, let us consider, let W be this vector, U, W1, W2. Again, this is a vector in R2. And we want to show, we want to look at this guy, U, the inner product between u and v plus w. And let's compute this by the definition, the way it's defined. Keep in mind, by the way it's defined, the inner product between u and v, as you can see, is u1 v1 plus 2 u2 v2. So let's do it in this case. It will be u1 times v1 plus w1 plus 2 times 2u2 times v2 plus w2. Right? This is just by applying the definition of the inner product. And now let's do the algebra here. If we do basic algebra, this will be u1 v1 plus u1 w1 plus 2u2 v2 plus 2u2 w2. Right? And now let's group them together. Let's do this in a smart way. So we'll have u1 v1 plus 2u2 v2 plus u1 w1 plus 2u2 w2. Well, guess what? This guy here, by the definition of our inner product, is nothing else than what? Than uv, the inner product between u and v, plus, and this guy here is nothing else, the inner product between u and w. Right? And that's what we wanted to prove, right? Okay. Now let's prove the third one. The third one, if k is any scalar, and like I said, I'm gonna emphasize the fact that it's a real scalar, then we have the following: k times the inner product between u and v will be k times u1 v1 plus 2 times u2 v2. And now guess what is going to happen? You're going to multiply them. So it will be k times u1 v1 plus 2k times u2 v2. Okay. And now clearly this can be expressed as, well, it's obvious. You can write this as k u1 v1 plus 2 k u2 v2, and this is nothing else than just k times ku times v. So we have shown that k times the inner product between u and v is the inner product between ku and v. Okay, and now the fourth one, well, we just have to do the inner product between v and itself. We will always the square of real non-negative. So basically we have that v is nothing else than just v1 squared plus 2v2 squared, which is clearly non-negative. Well, moreover, this will be 0 with equality. Let's mention that. With equality, if and only if v1 equals v2 equals 0, or the vector v is the 0 vector. Right. So this implies that this guy is an inner product space. So that's the proof. What we have defined here is actually it's an inner product. Okay, and we can generalize this. Let me point out this remark. This example can be generalized in the following way. Right? Instead of putting there the 2, we can put the constant. well, we can generalize in the following way. Let me mention it. So the inner product between U and V can be, let's say, K1 times U1 V1 plus K2 U2 V2 plus Kn UN Vn. So we can define it in this way for these Ki's to be greater than 0, with I going from 1 to all the way to n. So we can generalize it in this way. All right. Now, since we have seen two examples of inner product, let's see a function that is not an inner product. Example 3. A function that is not an inner product. Okay. Let's modify this the previous example, but this time we're going to consider something in R3. So this is example 3. In fact, we'll show that, let's state it directly, show that the function below, the following function, is not an inner product on R3, where, and let's define one these vectors. Let's say U is U1, U2, U2, U3, and V is V1, V2, V3. And we're going to define this product, this inner product between U and V as in the following ways: U1 V1 minus 2 U2 V2 plus U3 V3. You see, we can have all sorts of combinations, and we want to see if these. You see, you cannot just do any combination there and all of a sudden it will become an inner product. No, it's not guaranteed. You know, it's you have to set those 4 axioms are not easily satisfied, as we will see in this example. Well, in this one, for example, the last axiom is not even satisfied. So it's enough to show that one of them is not satisfied, right? Axiom 4 is not satisfied. Right? Okay. Well, how do we see that? Well, for example, let's consider the vector. I don't know, we can consider any vector, but let's say V to be, let's say 1, 2, 1. Okay. And now we would like to see, and clearly, the dot product between V and V, well, this is nothing else than just, well, let's call this, okay, V1 squared minus 2 V2 squared plus V3 squared. And now we're going to replace them, so it will be 1 squared minus 2 times 2 squared plus 1 squared. This guy, guess what? It will give us -6. And And as far as I'm concerned, this is not positive, it's actually negative. So that's it. This is not an inner product, right? Cannot define, this function cannot be, does not satisfy the axioms of all the axioms from the definition of an inner product. Now let's see another example, example number 4, and let me define this we'll define an inner product on the space of, let's say, 2 by 2 matrices. And we'll define the following way. Let's consider, let me consider the matrix A. And like I said, it's a 2 by 2. I'm just going to write the entries A11, A12, A21, A22. And the matrix B, we'll denote this by B11, B12, B21, B22, right? And these are B matrices in the vector space. And I'm going to call this V will be the vector space of all 2 by 2 matrices, right? We have seen this previously in previous chapters who this guy is. Okay, let me write again. The vector space of all 2 by 2 matrices with real entries. Okay, this is the, okay, and we'll define the following inner product. The function and let me define it in the following way. The inner product between A and B, these 2 matrices here, it will be nothing else than just A11, B11, A1 plus A12 times B12, no, times B21, sorry, plus A13 plus 8B, sorry, A22, A22 times B, okay, wait, I forgot about A21 here, times B12, and the last one is A22 times B22. In other words, if you look at this, this is nothing else than just the trace of A, B transpose, right? If you multiply, if you write a transpose of B, multiply A and B transpose, and you take the trace, you will get exactly this. This function is an inner product on M22, on the vector space of all 2 by 2 matrices with real entries. Well, I will leave it to you as an exercise to show this. It's not very easy to see. Well, pretty straightforward. I'm just going to mention a bit. Maybe I should, well, the first axiom, quickly, let me mention that we have to show that it's symmetric. Well, as you can know, trace, so this will be equivalent with trace of AB transpose is the same as trace of BA transpose, right? So that's very easy to see. Right? Okay. Okay, and the rest of the axioms are pretty easy as well. This, basically, the 2 and 3 will rely on the fact that the trace is bilinear as well. So the fact that trace of x of a plus b, let's stick to the notation, is the same as trace of a plus trace of b, and also that the trace of a scalar k times a is k times trace of a. So they rely on these two. And also the fourth one, let me mention that this will rely on the fact that trace of AA transpose, it will be nothing else than just the sum will be this the sum of the squares of these elements, a11 squared plus a12 squared plus a21 squared plus a22 squared, which again will be positive or non-negative. Okay, so this defines an inner product. Anyway, I'll leave the details to you. And now let's veer towards a fancy one. Well, example number 5. And here, finally, I will introduce for the first time in this course, like I said, I tried to avoid it as much as I could, but I have to do it because, like I said, what will follow will rely on this, and I will need this inner product space. This I'll define. Let's write it. An inner product space defined, an inner product defined on the space of continuous functions. Well, it can also functions defined on an interval AB. These are defined on a closed and bounded interval AB. Well, I can also relax this. I can just say the space of Riemann integrable functions. Anyway, I don't want to go into those details. So let's just write it explicitly. Let f and g be two real valued continuous functions in the vector space. And this time I will consider the following vector space. V will be CAB. So this is the space of all continuous functions, real valued continuous functions defined on this interval AB. So let's write it explicitly. CAB is nothing else than this set F defined on AB and real valued. F is continuous. This is the space of continuous functions. And here we want to show that this inner product, and let me write it in this way, between f and g, which is the integral from a to b of f of x times g of x dx. This guy is an inner product, defines an inner product on the space of continuous functions. Okay, right? So like I said, this is for the first time when we introduce some calculus. I want you to look at it. And again, if once you look at it, we have to verify those 4 axioms again, right? So the first one was to show that it's symmetric. Well, the inner product between f and g is, as it's defined as the integral from a to b of f of x times g of x dx. This will be the integral from a to b of, is the same as g of x times f of x dx. And of course, this is nothing else than the inner product between g and f. Okay, the first one is can be easily verified. The second one, well, let's look at this f, the inner product between f and g plus h. By the definition, this is nothing else than just the integral from a to b of f of x times g of x plus h of x. And again, in this case, we'll use a property from the integral, which supposedly you have learned this in calculus 1, or I'm not sure. Actually, I think in calculus 1. And once we use that, the fact that the integral is linear, this will be nothing else than just, if we multiply this here, let's multiply the functions inside. Sorry about that. This is the integral from a to b of f of x times g of x plus f of x times h of x dx, right? Which it will be equal to the integral of f of x times g of x dx plus the integral from f of x times h of x dx. But now if you look at it, this guy here, this guy is nothing else than just the inner product between f and g, and this guy here is nothing else than the inner product between f and h. Well, this is right, which is exactly what we wanted to prove. That's the second axiom. Now, the third one, well, let's look at this, the constant k times the inner product between f and g is nothing else than just k times the integral from a to b of f of x times g of x dx. Okay, and this will be, you can put the constant inside the integral, and this will be the integral of k times f of x g of x dx. Okay, and now clearly this is nothing else than just, if you want, you can write it in this way if you want, k f of x times g of x dx, and this is nothing else than just the inner product between k, f, and g. Again, the third property is verified. These are just easy computations, but the fourth one will be a little bit different. Now we want to see who is this guy. The inner product between f and f, well, it's the integral from a to b of f squared of x dx. And of course, since the function inside the integral is non-negative, right, f squared will always be non-negative, then the integral would be non-negative. And now the equality, that's the tricky part. With equality, if and only if the function is 0. Well, basically, well, I'm not going to go into details here, but I'm just going to explain it. The problem reduces to the following. If f is a continuous function, let's say a real valued continuous function on an interval AB, such that the integral from a to b of f squared of x dx is 0, then it follows that f of x is 0. And I'm not gonna prove this. It's a little bit involved. It requires some understanding about continuity. Basically, well, I'm just gonna verbally explain it. Well, if you assume that there exists an x naught for which this doesn't happen, well, by contradiction, we argue by contradiction. So this implies that if there exists an x naught in AB such that f of x naught is positive, let's say without any loss of generality, we can do this, then by continuity, f will be positive on a neighborhood around x naught. And since any neighborhood contains a symmetric neighborhood, you can say that f of x is positive for all x in, let's say, x minus, for all x in this neighborhood, x0 minus epsilon, x0 plus epsilon. Anyway, from here, you integrate, you just use the properties of integral, and you'll get a contradiction, something that 0 is greater than 0, because you will use this. Anyway, and we use this property for a function, this will imply that f squared will be 0, and therefore f will be 0. Anyway, I'm not going to go into details. This is a very nice exercise in, I would say, in an advanced calculus course. So if you, okay. So this will be a very important inner product space. Keep this in mind, because like I said, this will be very useful when we will talk about the Gram-Schmidt orthogonalization procedure, and you will see some properties with this inner product space for this particular inner product space. Anyway. Okay, now let's state the following theorem. Basically, this theorem will be about some properties of inner products. Okay, now let me consider that u, v, and w be vectors in an inner product space V, and let, well, as usual, K be any real scalar. Right. Then the following properties are true. Let me write them in red. The first one is the inner product between 0 and u and v. Let's stick to v. Is, guess what, is, since it's symmetric, is the inner product between v and 0, and guess what, this will give you 0, right? Now the second one, if we have something like u, the inner product between u plus v and w, well, guess what, this is the inner product between u and w plus the inner product between v and w. And the third one, this will be u, the inner product between u and k and v will be nothing else than just K times UV. Okay, these are the properties. Well, basically, it's just a consequence of the these properties are consequence of the definition, so there's nothing. And now, since we said at the beginning of the lecture, we tried to mimic the same thing as we did in the previous lecture. Basically, we're trying to define the length, the distance, and the angle between two vectors, but this time we're not in Rn anymore, we're in an abstract vector space. So let's do that. And after that, I'm gonna give you an example how to use inner product in for different functions in this space of continuous functions on an interval AB. Okay. Definition. In fact, maybe I should put definitions, and we'll define the following. We'll define the length, distance, and angle. Okay, great. The first one, the length or sometimes it's called the norm. Let's call it like norm. Okay. Of a vector u is, guess what, is the same thing, is given by this guy, which will denote it like this, which will be nothing else than just the square root between the inner product between u and u by the definition. So that will be, this is how we define the length of a vector u in an abstract vector space. Okay. The second one, so we want to define the distance now. The distance between two vectors, between, let's say, u and v, is given by, and we'll denote it in this way, distance between u and v will be nothing else than just the norm between norm of u minus v, right? And if you use the definition of the norm or the length, this will be nothing else than just the square root of the inner product between u minus v and u minus v. Okay. And now the third one, the angle between two non-zero vectors u and v is given by, and the formula it's pretty much the same, is the cosine of theta will be nothing else than just the inner product between u and v over the norm of u times the norm of v, right? Or theta between 0 and pi. So theta is the angle between the two vectors, right? Okay. And now I want to mention one other thing, a remark. The vectors u and v are called orthogonal if, guess what, the inner product between them is 0. So that's okay. Well, also if the norm of u is 1, then u is called the unit vector. Okay. At some point, we're interested to define the orthonormal vectors. Okay, and now it's quite clear that, well, we have seen previously that if we define this vector, the vector v, which is u and divided by its length, is a unit vector. That's obvious to see, right? The unit vector in the direction of v, let's say. Direction of v. Okay. Well, clear, since we let's look at the formula of the angle between two vectors, u and v. Well, as you can see, it's the cosine. And we know something about the cosine function. What do we know? We know that the cosine function is bounded, right? It's between -1 and 1. Well, this will imply one thing. Since we have this, since it is the way, as you can see, it's defined by this formula, it implies that the inner product between u and v divided by the normal of u times the normal of v is between -1 and 1. Well, you will see that this is what we call the Cauchy-Schwarz inequality. And we have proven this in the previous lecture. Okay, and now I would like to see an example. I would like to see how we're going to use this inner product on a specific example. And the example I have in mind, I think it's example number 6, is the following. And now use the inner product defined in example 5, I think. Yes, in example 5. So we want to use this. Okay. And the functions. And now let's define two functions. Let's just say f of x equals x and g of x equals x squared. And both of these functions are defined, f and g are defined on the closed and bounded interval 0, 1 and the real value functions. So we want to use this inner product defined in example number 5 and these functions to find the following quantities. The first one is we want to find the normal of f, and the second one is to find the distance between f and g. Wow, okay. And keep in mind that our functions are given explicitly. As you can see, f of x is x and g of x is x squared. Let's keep that in mind. Well, it's pretty straightforward what we need to do. Well, let's do it. As you can see here I have the length I need to find the length of a vector in my vector space of continuous functions. And here I have to find the distance. Right? Okay, let's set up the record straight right from the beginning. The vector space V is the space of all continuous real value continuous functions on AB. So this is the vector space. And the inner product, which was defined in example number 5, is given by this is the integral from a to b of f of x times g of x dx. This is the inner product. This is the inner product on my vector space of all continuous function, real valued continuous functions on defined on the interval AB. Okay, and now it's quite clear what we need to do. Keep in mind that the functions, let's not forget that f of x is x, and g of x is x squared, and f and g are, oh my god, this is not AB, this is 0, 1 here, I'm sorry. Integral from 0 to 1, and again this is C 0, 1. Okay, and these are defined on 0, 1 and they're real valued. Clearly these are continuous functions. F and G are continuous functions. Okay, since they're elementary, it's obvious. Okay, this is calculus 1 for sure. And now we need to compute its now the length of f, or the norm of f, is nothing else than just the integral from 0 to 1 of f squared of x dx, which is nothing else than just, since f of x, is the integral from 0 to 1 of x squared dx, which is x cubed over 3 from 0 to 1, which is nothing else than 1/3. So the norm of f, or the length of f, is 1/3. Wait, the norm squared, right? Right, because the norm of f is the square root of the inner product between f and f, right? We've said this. Okay, so this implies the norm of f, if we take the square root, is nothing else than just 1 over square root of 3. Okay, that's the first part. Now the second part, keep in mind that we need to find the distance between two functions. What I'm going to do is I'm going back to the definition. The distance between f and g was nothing else than just the norm of, or the length of f minus g. What I'm going to do, I'm just going to compute just like I did on the norm of f. I'll do the same thing, but this time I'm going to compute the square of the distance. So this will be the distance between f and g, and let's say this is squared, is nothing else than the length of f minus g squared, which will be the inner product between f minus g and f minus g. And this guy will be nothing else than just the integral from 0 to 1 of f of x minus g of x squared dx, right? And now I'm just gonna, we know who f of x is, or who g of x is. Now we're just gonna plug them in. So this will be the integral from 0 to 1 of x minus x squared and everything squared dx. And well, if we do the computations now, oh my, this will be nothing else than just the integral from 0 to 1 of, okay, let's do it. X squared minus 2x cubed plus x to the 4th dx. And now applying the properties of the integral, basically that the integral is linear, this will be nothing else than just the integral from 0 to 1 of x squared dx minus the integral from 0 minus 2 times the integral from 0 to 1 of x cubed dx plus the integral from 0 to 1 of x to the 4th dx. And this will be equal to x cubed over 3 from 0 to 1 minus x minus, minus 2 times x to the 4th over 4 from 0 to 1 plus x to the 5th over 5 from 0 to 1. And all this mess here will give us, let's say 1 over 30. Okay. Well, since we computed the distance, the square of the distance, this implies that the distance between f and g is 1 over square root of 30. And that's it. Okay, now I want to mention something. Because since we talked about the length and the distance, right? We talked about these two here. I want to mention some of their properties. I'm going to divide them like this. Properties of length, so that the picture will be very clear, and this are the properties of distance. Okay. The first one is that the length of a vector u is always non-negative, and here that the distance between u and v, since it's defined as the length of u minus v, will always be non-negative as well. Well, with equality for the first one, when in the first case, it will happen when u is the zero vector, and the equality in the second case, where the distance will happen if and only if u equals, the two vectors u and v are equal. The second one is that, well, I already said it, but anyway, the normal view is 0 if and only if the vector u is 0, right? And the same here, d of this distance between u and v is 0 if and only if u equals v. And the third one is that the length of any constant k times u is the same as constant, the absolute value, sorry, of the constant k times the length of u. And here will happen, the distance between u and v will be the same as the distance of v and u. It's symmetric. Okay. Right? That's what I wanted to point out. So these are the two properties of, and now, like I said at the beginning, I want to veer towards something very, very important, because I would like to use this kind of properties when I will define the orthogonal projection of a vector onto another vector. And I think this is also done in RN, I think, in the Calculus 3 course. I'm not sure about it, but probably Yes, this is well. Okay, and now I would like to talk about what we mentioned at the beginning of the lecture about the Cauchy-Schwarz inequality, about the triangle inequality, or about the Pythagorean theorem. Okay, let's see that. Let's mention this. We have the following theorem. I don't recall the number, anyway, whatever. Let's consider that U and V be two vectors in an inner product, in an inner product space V. Okay. The first thing that happens here is the Cauchy-Schwarz inequality. And we have seen this for the dot product in Rn, but the same inequality holds true, which says nothing else than just the absolute value of the inner product between U and V is less or equal than the length of U and the length of V. That's the inequality. Maybe I should, yeah. Okay, no, maybe I should write it. Right? This is the Cauchy-Schwarz inequality. Okay, the second one is the triangle inequality. Which says the following. It's the same as we stated in for the dot product in Rn. Basically says that the length of U plus V is less or equal than the length of U plus the length of V. Okay, and the third one, which is very important, is what we call the Pythagorean theorem. Which says that U and V, U is perpendicular or orthogonal to V, so U and V are orthogonal if and only if we have the following. The length of U plus V squared is the same as the length of U squared plus the length of V squared. In fact, all right, so these are the three results that we need to know. The Cauchy-Schwarz inequality, the triangle inequality, and the Pythagorean theorem. Keep in mind that for the Pythagorean theorem to hold true, those two vectors must be orthogonal. In other words, their inner product is 0. Now, let me talk about something else, which will be relevant to this. And now we're going to talk about orthogonal projections in inner product spaces. So we're going to take a vector and we want to project on another vector. And you'll see that will be very important here in inner product spaces. Okay. What I'm gonna do now, let me consider let me consider two vectors in Rn. So let u and v be two vectors in R2, in fact. So let's see in the simplest case what happens. Okay, now if v is non-zero, then u can be orthogonally projected onto v. Can be orthogonally projected onto v. And let's see what this means. I want to draw a picture. Because I want to be, what does this mean? As in the following picture. Okay, and let's draw the picture. Okay. This is my vector v, right? And let's say this is my vector u, right? Okay, okay. This is my vector u. Okay. And now what I'm going to do here, this is my angle theta, right? And what I'm going to do here, I'm going to project. So the vector u can be orthogonally projected on vector v, right? And we will denote this guy. So this is the picture. This projection is denoted by, and we're going to write it in the following way, as the projection of u onto v, right? Which will be nothing else than just, well, let's say a scalar a times v, right? And we can actually compute this, right? This and the way we're going to compute this will be in the following way. Now, let's look at the case when a is positive. If a is positive, then you see that the angle here, the angle theta is positive, right? Oh, sorry, the cosine of the angle is positive. The cosine of theta is positive. Okay, great. And we have that this guy, the length of AV will be, by the definition, is the absolute value of A times the length of V, right? But we know that this is positive, so it will be just A times the length of V. But the A times the length of V, if you look at it, this is nothing else than just U, the length of U, times cosine of theta. right? Keep in mind that the triangle, it's a right angle triangle. Okay. Okay. And now, if we write the cosine by the definition, this will be nothing else than just the length of u times times the length of v times the cosine of theta. Let me write it this way. Let me divide and, okay, let me do it like this first, and then we'll write a formula. Let me multiply and divide by the length of v. And this guy is nothing else than just the inner product or the dot product, because since we're in R2 right now, between u and v over the norm, the length of v. Which implies that let's see, what does it imply? Which implies that A, this guy A, the constant is nothing else than just u dot v over the length of v squared. Or if you want this, it's u dot v over v dot v. So finally, we have the formula that the projection of u onto v will be nothing else than just u dot v over v dot v v. That's the formula. And in fact, this happens as you can see. We said at the beginning that u and v are two vectors in R2. So in this case, the inner product is in fact the dot product. Okay, now we have seen this case when A is positive, but when A is negative, let's see, what do we have? If A is negative, in this case, we have the following. Let's see. Let's draw the picture. Then the orthogonal projection. Of u onto v can be found using the same formula basically, but the picture will be just a bit different using the same formula. And the picture is a bit different. Let me draw it so that you can understand it perfectly. This is this is my vector u. This is my vector v here. Vector v. Okay, and now the angle theta will be this guy here between them, right? And now once I project here, the projection of u onto v will be, again, the constant a times v, but this time the constant is negative. Anyway, it's the same formula. And now let me give you a quick example, and this story happens in R2, right? But the question is, we want to replicate this in a much more general setting, and we'll see how that will go. But before that, let me give you an example. Example number At this point, I lost the number of examples. Number 7. Let's see a quick example. Let's in R2, let's pick 2 vectors, and the orthogonal projection of, let's say, a vector, let's say 4, 2 onto the vector v 3, 4 is given by the following. We have the following formula. So the projection of u onto v will be nothing else than just u dot v over v dot v v. Right? This is the formula, and this will be equal to, well, we compute this, so this will be 4, 2 dot 3, 4 over 3, 4 dot 3, 4, and everything you multiply by 3, 4. Anyway, once we compute all this mass here, this will give us 12, 16, okay, so it will give us okay, 20 over 25 times 3, 4, and if you want to plug it in, this will give us 12 over 5 and 16 over 5. Okay, that's the figure. If you want, we can draw a picture so that you can see it clearly. Actually, that would be great. So let's draw a picture. So let's have this, we have the vector, let's say 3, 4. Let's say this is here. See, this is the vector u is 3, 4, 4, 2. This is my vector u, let's say. Well, it's kind of shorter a bit. Okay, this is my vector v. This is my vector u. Here it's 3, 4 for v, and this is 4, 2. And now I'm wondering about the orthogonal projection. Well, guess what? If I project here, let's say I project it like this, this guy here will have coordinates, guess what? 12 over 5 and 16 over 5. That's the projection. Okay. And now let's see the definition of orthogonal projection. And guess what? The same definition holds true for if we replace R2 by Rn, or even better, if we replace it by any inner product space. Let's consider u and v be vectors in an inner product space such that, let's say, v is non-zero vector. So I want v to be non-zero. Then the orthogonal projection of u onto v is given by the following. Well, the formula is the same. We're going to denote this. The orthogonal projection of u onto v will be nothing else than just the inner product between u and v over the length of v squared v. That's the formula. And again, you can, this is valid, like as you have seen in R2, in R3, in Rn, and so on. Well, I want to point out a remark before. Well, it's quite if U is a unit vector, so if V is a unit vector, keep in mind that the unit vector has its length equal to 1. And then the projection formula will have a simple form. The projection of U onto V, where V is a unit, will be nothing else than just the inner product between U and V times V. Oops. That's the formula, right? Okay, and now there is one last thing that I would like to talk about. Maybe an example, and then I'll stop here. Is the following. I want to talk about is the following theorem. And the following theorem will address the following issue. We want to see how the orthogonal projection and the distance are related to each other. So this will involve the orthogonal projection and the distance. Okay, it says the following. Let me consider again, let U and V be two vectors in an inner product space such that V is non-zero. Then we have the following formula. The distance between U and the orthogonal projection of U onto V is less than the distance between U and a constant K times V, where this constant K is different than the inner product between U and V over the length of V squared. So this holds true. This inequality holds true. Well, here, well, I don't want to waste any time doing the proof of this. I will just briefly mention the proof. Well, basically, you just have to write the distance formula and also the orthogonal projection formula of U onto V. And then at some point, you will use the Pythagorean theorem because some of them will be, you'll see that these two vectors will be orthogonal there. And everything will follow from the Pythagorean theorem. Anyway, now let me give you one last example and then we'll stop here. I think this would be example number 8. And this example will concern finding the orthogonal projection in the space of the continuous functions, real valued continuous functions defined on the interval AB. Let's consider f of x to be, I'm going to take to be the constant function 1, and g of x to be the identity, g of x equals x. And in my vector space, like I said, C, which is C of 0, 1. Now what we want to find the orthogonal projection of f onto G. Okay, let's set things straight here. Keep in mind that the vector space, again, V is the space of continuous real valued continuous functions defined on the interval 0, 1, and the inner product, this is the vector space, and the inner product between f and g is given by this, the one from the example number 5. On our vector space, right? Now, look at the formula. You see, now we're going to use this formula, right, the definition, so to find the orthogonal projection. And now, let's see, what do we know? We need the inner product between f and g will be what? Will be the integral from 0 to 1 of, and in our case, will be f of x is 1 and g of x is x. This is nothing else than just the integral from 0 to 1 of x dx, which is x squared over 2 from 0 to 1, which is 1/2. Okay, great. And now I'm going to compute the inner product between g and g. In other words, this will be nothing else than just the length of g squared, which was nothing else than just the integral from 0 to 1 of what? Of g squared of x dx, which is g of x is x. So this is the integral from 0 to 1 of x squared dx, which is x cubed over 3 from 0 to 1, which is 1/3. Okay, great. So the orthogonal projection of f onto g is given by the following. Let's write it. So it will be the inner product between f and g over the length of g squared times g, which is, again, this will be a function. So the inner product here will be 1/2, we have seen, 1/3, and g of x is, as we know, is x. So this will be 3 over 2 times x. That's the function. And that's it. Okay, guys, I think I'm going to stop here. Thank you very much.